Okay, welcome back. I hope you had a good Easter. Got some holiday also, I hope, not only studies and re-exams. Okay, time for module 6 on boundary value testing and its related analysis and testing techniques. So last time we talked about black box testing in general and showed some examples. Um, and today we focus on boundary value testing. So we discussed that there are many black box testing techniques. Of course, black box means we're not looking into the code itself. We're considering the thing, the software, the function, the class that we are going to test as a black box. And we look at the interface, we look at the specification requirements, and we try to create good test cases from that. And all these techniques, they are about selecting the specific inputs, the specific test cases that we're going to use. They in themselves don't help you with the oracle, right? So the oracle will be based on the specification and requirements. But these techniques help you select which inputs, where to consider, look for the correct behavior, or the wrong behavior in that sense, also of the thing that you're testing. So we discussed a little bit random testing last time, and some other techniques. And today we will focus on boundary value analysis, boundary value testing, and the connected techniques that you need to understand in order to use it, in particular equivalence, class partitioning. The cause and effect graphing, state transition testing are more related to model-based testing, which will come in later modules of the course. Error guessing is also heavily related to boundary value analysis, so we'll discuss that some more. So just as an overview, I showed you this slide last time also. Boundary values is based on the idea that you first identify equivalence classes, and I'll show you more later today. So what are the big connected chunks, classes of inputs where we expect the software to behave similarly to each other in the same way, basically, right? It will go through the same logic for all the elements of that class. That's an equivalence class. So we have equivalent behavior of the software for inputs in this class, right? The boundary values are to check the values that are on the border between two different such classes, right? And why this is important is because somehow when we write the code, when someone writes the code, they will have to also consider these boundaries, because that's where the behavior should change, where the processing, the stuff that happens in the software is going to change when we traverse this boundary, when we are close to it, when we're over it, right? So also the problems are likely to happen in these areas. Rather than looking at the whole class, there are many values sort of in the middle of the class, but in general, people tend to make mistakes when they are switching, when they are going between different classes of inputs. And that's what it's based on. So just as a recap, and error guessing is very similar, but there we try to guess, or also inside a class there might be some parts of it that are more error prone. So typically on the border between 0, large values and so on. So error guessing is more about guessing about internal processing and where things can go wrong, while boundary values is more systematic, let's say. But first, we need to do equivalence partitioning. So we need to partition, to make into parts the input space, and to understand the input space and where we have important different classes of inputs, right? So first, be very clear when you're using equivalence partitioning. to define the input space. What are the allowed inputs? What are the boundaries sort of this space? So this can be based on the types, it can be based on specifications, putting limits on the inputs. For example, it could be that it cannot handle an empty file. It has to take a mail address as input. All of these things helps you define the input space. Then the second step in equivalence partitioning, so partitioning into equivalent classes with equivalent behavior. Then we start by looking at the rough classes, which are valid and invalid classes, right? So this is sort of a basic delimitation. That of course there will be a boundary between what is valid inputs, all of the valid inputs, and what are not valid, right? Positive numbers, strings that need to have a certain format, strings that need to be a certain length, files that need to be a certain length, files that cannot be larger than some limit, and so on. All of this can help you understand better the valid and invalid classes. And then in equivalence partitioning, when you have done this, you can also go into parts of the valid class and define that. So that would be stepwise refinement. So now when we identify the invalid, we now look more into the valid ones, or we can also look more into the invalid ones. There might be subclasses to the invalid ones, and there are definitely always almost subclasses to the valid input space. And then in equivalence partitioning, you now focus on the valid and you select some input and create a test case from that in each class, in the valid and in each class of the invalid. And after that, you can also consider combinations of the different equivalence classes, different partitions. And then, of course, you go on, you write up your test cases, you run it, and you observe if the actual outcome of the software is what you expect. So this is a very generic definition, and of course it comes down to how do you partition, how do you split things up. And one way to do this is, of course, to look at the specification. And as we've discussed before, sometimes the specification is very detailed, sometimes it's not. When it's not, you have to go from your experience by talking to customers and so on, and you try to clarify the specification. Sometimes you can have a written down, very specific, detailed, explicit specification, and then you can go directly into input partitioning or equivalence partitioning. So basically it's about, if you look on the bottom here at the input space conceptually as this box, then you're trying to find the different blocks, major classes where the inputs are similar. And the assumption in input partitioning or equivalence partitioning is that all inputs within one class, like B1 here, are equally good to become test cases, right? And why we are going to identify equivalence classes is because we don't want to take 1,000 test cases or inputs from B1 here and forget about B2 and B3, right? So we want to take only a few in each class, and then we must first identify the classes. Mathematically, it's important that the partitions or the classes are disjoint so that they don't overlap, right? Disjoint means that they are separate, like B1, B2, and B3 here. They are separate, they don't overlap. In practice, it's very common that you cannot fully, or it's not worth it to have disjoint partitions. So you see it more as identifying important parts of the space, and it's not worth it to spend a lot of details as writing down the logic to make it disjoint. But sometimes there is, and it's important to know the difference. So formally, mathematically, a partition means that they must be disjoint, and they must also be complete. So if you add them together, they will fill the full space. So this is the sort of ideal and best equivalence partitioning. And then typically you write test cases so that for all inputs in one class, you write the test case so that they will lead to a pass or to a fail, right? So this is the idea. The idea with identifying them is that a single one can help you find the faults and failures for all the values in that class. And that's the basic assumption, and that's why it's sort of a basic technique. Of course, in practice, a software has multiple characteristics, and they will not be disjoint. They will create more complex and partly overlapping classes. And you have each characteristic or property creates a different sort of partitioning in a sense. Here, for example, we have one characteristic is that the order of a file that the software takes as input can be sorted in inverse order or random, basically arbitrary order. Characteristic 2 is about the length of a password. Characteristic 3 is about other restrictions on which characters can be used in a password in order maybe to process the file. So you see here that when you have multiple arguments to a piece of software, there can be complex interactions between the arguments that creates classes of more complex sort. If we take only C1, the characteristic 1 here, we have 3 different ways that the file can be ordered, but we can see here that they do not make for a mathematical partition. So, for example, B1 sorted in ascending order from high to low, and B2 would be sorting in the opposite, inverse order from low to high. Well, if the file length has only a single zero or a single element, then they actually overlap, right? So you see that there are complex interactions in the inputs that can lead to not overlapping classes like this. And actually, something of length 0 or 1 is also sorted in arbitrary order. So they all overlap for all inputs of length 1 and for the empty input, right? So they are not disjoint, but of course this is more of a mathematical nuance, and the important thing here is that so you would, in this case, you would first split the space into length 0, length 1, and then length over 1, so 2 or more. Now you have 3 classes, and within each one you can now look at the different sorting. So for the length 0, the sort order doesn't even make sense. For 1, they are all the same. And then for length 2 and above, the order is partly overlapping, because sorted in arbitrary and sorting in disordered can also overlap there. But as you go along, you can refine it further into more detail. The distinction between valid and invalid is an important one, and but also other classes. So in some sense, it all comes down to understanding the input space and dividing it up into meaningful and doing an analysis of that as a human. based on the specification, based on your experience, based on the information you have at hand, define what are the important classes of inputs, and then take different combinations of them, right? This is the benefit of doing this type of analysis. So this can be called combinatorial testing. So once you have an analysis of the into different classes, you can do many different combinations. So all combinations coverage means that you ensure that you cover all combinations of the different classes, in a sense, for different inputs or conditions. And this is often like in structural testing, the path coverage is often too complex to, and then all combinations coverage on the black box side is also often too costly, because there are too many. Even if you have few classes, the number of combinations, if you want to take all of them, can be too large. Each choice is a different one, which is more realistic. And then there's a lot of research on pairwise coverage and t-wise coverage, which means t here can be a value larger than 2. If t is 2, then we have pairwise. You're considering a pair. If t is 3, you have triple-wise or triplet-wise coverage, and t can go higher. And there's a lot of research on how do you find the sort of fewest test cases that ensures a certain level of t coverage. So this means not taking all combinations, but downsampling that to run fewer test cases and still trying to cover as many combinations of arguments or classes as possible. And then base choice is a very basic one. So you see, again, you're very structured in defining your classes and doing your analysis, and then you can sort of define what level of coverage of these classes and their combinations that you want to do. Let's take an example. Let's assume 3 characteristics with blocks Q1. So you can have for one characteristic Q1, you can have basically 2 classes A and B. For the second one, Q2, you can have 1, 2, or 3, and for Q3, you can have X and Y, right? So basically for block 1, defined by Q1, you can have 2 combinations. For block 2 should be 3 there, yes, and block 3 you can have 2. So if you take all combinations coverage, all combination of the blocks from all characteristics must be used. So this means 2 times 3 times 2, meaning 12 test cases here, right? And this is of course possible, 12 test cases in this case, but you can easily see that if we have a lot more classes within one of the conditions, this will quickly grow. Or if you have many more than 3 different characteristics, this will also be very impractical. Each choice, much simpler. Then again, we are just going to look at each block and ensure that we cover all the different classes within that condition in that block at least once. So here you can see that we had A, B in the first one, and if we look at these 3 test cases here, we see that both A and B have been selected at least once. The second one we have 1, 2, 3, and here we see then we need 3 test cases to cover 1, 2, 3, and then for the last one we need to cover 2. So you see that these 3 test cases cover each choice of the 3 different characteristics or classes here. So it's much less costly than all combinations, but it also gives you, it's less automated. You need to choose among many possible test cases here. But of course, this is a critical thing that you will do when you actually do combinatorial testing. And you saw in my practical testing video the previous week that I tried to, within each class, I actually tried to vary. I varied the floating point numbers that I used to cover more of the class, even though I was ensuring A, B. I would probably, instead of selecting the same value from A, the class A in this case for the first characteristics, I would try to take different values just to get even better coverage of that class, right? Pairwise coverage, then we take pairs of the classes. So, for example, the first one and the second one, then we have, and we look at all combinations of pairs, right? So we would have A1, A2, A3. This is selecting the class A for the first characteristic and then combining that with all three classes for the second condition, right? That gives you A1, A2, A3, and then you vary to B for the first one, and you get B1, B2, B3. And you do the same to ensure all pairs are covered. Then you have a list of all the pairs, and now you can select, you can combine them. So now you're only going to select fewer test cases to ensure that all the pairs will show up in the test cases you actually select. And here it's enough with, what is it, 8. If these 8 test cases, if you take each pair and you look at one of the test cases, you will find it. So the combination A1 is in the first test case, A2 in the second, A3 in the third. Then the same for B1, B2, B3 are also there, and then so on, right? And then T-wise coverage will be the same, but then you start with triplets instead of pairs, or quadruplets instead of pairs, and so on. And you can imagine that this becomes an optimization problem, and we can use optimization tools or search to search for the fewest number of test cases that covers pairs or triplets or quadruplets. And there's been a lot of research showing that if you go up to, if you go from single, each condition coverage would be a single, up to pairs, up to triplets. When you come to quadruplets or quintuples, so 5 combination, 5-wise, quintuple-wise coverage, after that you tend to not find more faults in real systems because people don't tend to write software that is that complex. It can happen. There are examples where it happens. But if you focus on like 3, 4, 2, 3, 4 is where the bulk of the failures are. So, if you have more money to put on testing, you can go higher. But you can imagine that there's a lot of tools to help you do this. Base choice, then you have like a base choice and you vary the other ones for that. So, different techniques to just again get down in the number of test cases while still trying to cover from different aspects the classes that you have identified. Let's take an example here. We have an example where this is the specification as written in the requirements. Employees receive 50% of their monthly salary as a Christmas gratification. So this is some kind of salary management system, some kind of database with some interface and some simple calculations to help companies handle the salaries. And when employees have been for more than 3 years, they get an extra Christmas salary gift, more money in the Christmas salary. Employees that have been with the company for more than 5 years, they receive even more, so a higher bonus, Christmas bonus. And in case they've been with the company for more than 8 years, they get a full extra salary in December, right? And then there are different brackets, so levels somehow of employees. G1 is the normal, G2 is middle manager, and G3 is the higher management. So, and the G2 and G3 gets an extra gratification, extra bonus on top of the rules we saw above. So you can imagine that, okay, this is a little bit hypothetical, but you can easily imagine that this type of situation happens in a lot of software systems. And G1 don't get an extra gratification, right? Because they're not managers in this example. So characteristic 1 is the time within the company. So we're imagining here that we're going to test the system, and somehow the time that you've been with the company is important. We saw that from the requirements. So the duration in years. Characteristic 2 that is important in this for this functionality is the bracket, right? Time and bracket. That seems to be able to determine what kind of Christmas salary bonus you will get. So somehow the system must have a function or somehow encode that given these two inputs, the time within the company and the bracket, you need to calculate the bonus level, right? So what are the equivalence classes? We have the two characteristics, how long have you been with the company, which bracket are you in, and then we identify classes. And from the requirements, we can see, okay, first we see that negative time is impossible, right? So we have an invalid equivalence class, which is the number of years is less than 0, right? You can be 0. You can start on the day that this calculation needs to be done. So in years, we go from 0 up to 3 years. Then we are in one valid equivalence class. Below 0, we're on invalid equivalence class. The next one was between, so higher than 3, but less than or equal to 5. That was the second valid equivalence class. The third one was between 5 and 8. And then we assume that you cannot work more than 50 years, because then you will be, even if you start at 15, say, you will be 65 if you stayed 50 years. And so let's assume that then you will be retired. So the fourth valid equivalence class for the characteristic, how long have you been with the company, is from 8 years up to 50 years. And then we get an invalid equivalence class of X being over 50. Of course, if we change 50 to, say, 70 at least, then that could also be an invalid equivalence class. So if you're unsure, you can, of course, add more classes, because this is just an analysis tool, right? It's not a God-given how it's implemented or that it's truly true, right? So you can always in testing, you should push the boundaries. So you could add another equivalence class, because a class is just an analysis, our view of what is important, what can be important. So we can add more, but here we stayed with up to 50. So we got 6 different classes here, only for characteristic 1. And then for bracket, we have, well, the 3 brackets. So this was discrete, so it's very simple. We have 3 valid equivalence classes, and then we have an invalid equivalence class, which is you are in some other bracket, which was not one of these 3. And we have high-level classes. So you can see that the valid class for characteristic 1 is between 0 and 50, and the valid bracket is G1, G2, G3, and then it's true. And then we have the sub-partitions that we discussed. So how are we going to test this? Well, now we can select the techniques and combine them to get different levels of testing. If we take each choice, we are going to ensure that we've covered all the classes at least once. And how many did we have? We had 6 for the first one and 4 in the second one, so we had 10. And if you look at these, 7 test cases, they cover all of them. So G4 here is sort of the other bracket. So we go through, basically we select some, for test case 1, we sample some value in the 1.1, so the first equivalence class from 0 to 3, we select 2 here, and then the bracket, should be a T there, G1, then we've covered 1.1, equivalence class 1 in the high level class 1, and equivalence class 2.1, which is the first one in the second high-level class. And then we go through like this, and we sample inputs in each class, and we ensure that all of the classes that we identified on the previous slide have been covered. So we have 1, 1, 1, 2, 1, 3, 1, 4, that's 4. We have 2, 1, 2, 2, 2, 3, that's 7. And then we have the 3 invalid ones by selecting -1 year, by selecting 83, which is more than 50, and by selecting G4, we cover the invalid ones. Okay, so this now was equivalence partitioning. And you will see also in SCTP, the book, they go through this in some detail. Now, the basic premise there is that any input in a class is equivalent. So we selected 2 for the first class in 1.1 in the example, but we could have selected 1 because 1 and 2 are both in between 0 and 3, which was the limits of that class, equivalence class. In boundary value analysis, we select on the boundaries or right next to them, right? So the boundaries for that class between 0 and 3 is 0 and 3. So we should select 0.00001, 0, and maybe minus 0.00001. And we should be just on and right on the inside or outside of the boundary. That's the addition of boundary value analysis. So it's still based on an analysis of equivalence classes, but you don't make the assumption that all values in a class are equivalent. We assume rather that it's more difficult to get it right on the boundaries. For example, if the code was written with a slightly wrong value for detecting the boundary based on the inputs, that could lead to problems and failures, right? So the basic assumption in equivalence partitioning, which is in its name, equivalence, if that is not true, which often it's been found it's not, then we need a smarter way to select the test cases once we have identified the classes. So boundary value analysis is an add-on, an improvement on equivalence partitioning. So here we can have an example if the entry field X in a user interface expects a signed integer. So an integer which has a sign, so plus or minus. We can directly see maybe that there are 3 equivalence classes because we happen to know that this is a 16-bit, or I don't know, is it even 16? No, it's not. It's 14 bits. One is used for the sign and whatnot. Anyway, let's say we identify that minus 16,384 up to 16,383 because of the way numbers are saved and processed in this system is a valid class. Then we have values below those outer limits are invalid equivalence class 1A and 1B, right? So from the equivalence classes, we can select 3 test cases. So we sample some random number in the valid one, and here we selected 13,566. We sample one in the class 1A, which was minus 17,000, and then from class 1B was 18,000. But the boundary values, now the boundary value testing or analysis tells us we should also test right on the boundaries and right next to it. So for integers, it's easier to see, right? You go right outside the boundary, on the boundary, and right inside on the lower bound. So every bound that you know of, you will do this. And then you do the same on the upper bound. So you get more test cases doing boundary value analysis, but it's known that people tend to, or programmers tend to make one-off errors or misunderstand where the boundary is, or there's some complex calculation in determining the boundary, then it might be hard to get it exactly right. So that's why. Special values can also be seen. So 0 is like the prototypical boundary. something happens in computer software at important boundaries, and 0 is one such boundary. So trying values around that boundary can be good. Also, even if you don't see a clear reason from the specification that this would be an equivalence class, you can decide that it's an important one because that's where people tend to make mistakes, and so on and so forth. Yeah, and this we go on here, valid equivalence class. So we could use the 0 to split it up into different, more refined valid classes, and also we add maybe an invalid equivalence class 1C here, which is if this is a text box, maybe you're not even providing a number, so we can, or people might misunderstand and try to write down in alphabet characters a number like 10. That is, in some sense, a number semantically, but it's not a number in the typical format that a computer expected, maybe. So this could also be a different type of invalid input that we need to test. So this is, you see that it's still based on your experience, it's based on the specification and requirements, but it also kind of the amount of effort you put into the analysis also defines what are the equivalence classes and thus which boundaries to consider. Now, a problem with this boundary value analysis is that this is about it, right? I mean, this has been one of the key testing techniques since the 80s, 70s going forward, but you can't find it sort of defined in more detail than this. It's still based on manual analysis of inputs and defining and identifying these equivalence classes. So in the last couple of years, me and my research group has been trying to how do we automate boundary value analysis? How do we automate boundary value testing? And we've proposed actually from this year, my postdoc Felix Dobslaw has proposed, together with me and some other colleagues, a boundary value exploration method, which is an automated way to help you find boundaries. And just to give you a little bit of sense here of how that could work, here's an overview. So this is something from our recent paper, and on the bottom you have two techniques that we use, so automated boundary detection algorithm, and we use also software visualization. Both of these two techniques help you explore the boundary values. So how do these three concepts relate? So you have boundary value analysis, which is sort of the manual analysis of where are the classes and thus where are the boundaries. Boundary value exploration, which is the general technique we propose, can automatically find candidates for the boundaries. So it can help you find interesting values in the input, which you can consider in your boundary value analysis. So it can help you interactively to refine your analysis. And once you have defined equivalence classes in the boundary value analysis, you can then write test cases. What are using the specification or your knowledge of the requirements on the left on top here. You can write down what are the expected, and then you can run test case and compare what does the implementation on the top right actually give you. And this comparison is the test case, right? So the boundary value testing uses the output from the analysis, which is helped by the exploration, to do the actual boundary value testing. So this is our general framework, and formulating this in this important way is important, because then we can now introduce more and more techniques that help you come up with good candidate boundaries, right? So we can base it on previous systems, we can base it on automatic techniques and so on. And in the last couple of years, we've come up with some ways of doing this. And we do it by looking at derivatives. So this is the key idea. If you remember math, your calculus math. Maybe some of you do, maybe some of you it's long forgotten. But anyway, if you have a function that takes an input x, which is a number, a mathematical function of x is some calculation inside to give you the output f of x, right? And here we see an example of such a curve. And of course, in mathematics, this is very limited because inputs to this software here, function, is only one number, and the output is only one number. So this makes it easy to analyze, and we can do all kinds of powerful things in mathematics. But this is hard to use for software because we have more complex inputs, more complex outputs, and so on. But stay with me. So the idea of a derivative of such a function, a simple function in mathematics, a continuous function of numbers returning a single number, is that we can define the derivative in a point x. We can get that by adding a small delta called h in this formula. So we add a small delta h to the x we had, and we calculate what is the output from the function. So f x plus h, and we subtract the f of x that we had. What was the original output here? And then we divide by this small delta. So if we make delta smaller and smaller and smaller, we're going to get a derivative in that point, which is basically how much is the change in this point, A in this case here. How quickly does it change? You can imagine, even if you take a very small h, if the curve is going very quickly up and down, then the derivative will be higher. So it's more sensitive to even small changes here. And I proposed a few years ago and in a paper last year that we can generalize this idea to take the derivative of a program. So first, look at the function here. You can see how the derivative is 0 when we're switching around. And then here, now it's getting close to 0. It's very level, not much change, not so sensitive. Now it's going up, so positive, going higher, higher. 1 point, almost 2. Now it will be going down, will be turned, and now it goes steeply. So a lot of changes here. This is some kind of boundary, right? Now quickly up again. So you can see here how the derivative of a function is tracking the sensitivity to change. And this is what I proposed in a paper last year, that boundaries are where a program changes quickly, where a program is sensitive to small changes in the input. So basically, mathematically, we can then generalize the derivative of a function in mathematics from calculus to a program derivative. So given two inputs, A and B, we are now going to use the same shape. So call the program. Here we call the program F. Below we'll call it P. So check the output for the input A, subtract the output somehow of the input B, and then divide by their difference, right? So the difference is the delta. So it's the same shape, but of course we cannot use minus. We must use something smarter. And from information theory, there are distance functions that can work for any information. And if we use those, we can define the program derivative for a program at input A. So this is a parameterized derivative, and you need to give it two distance functions, one for the output, one for the input. Then you calculate the output of the program in A and in B, and you use the output distance to calculate the distance, and you divide by the input distance. So this is a general way of finding boundaries now. If we try to find the largest values of the program derivative, in some sense that's the most sensitive part of the input space, so we can use it to find boundaries. So in this paper with Felix, we use this on a date library in Julia, but we can also apply it to Java, and otherwise it's a fully general way to do automated boundary value exploration. And here you can see, here we varied the day of the month and the month itself, and visualizing the value of this program derivative, we can see that it has the highest value here on the boundaries. So you can actually visualize here, because it's a simple example, where the boundaries are, and now without having the information from the specification, automatically we can find these boundaries. So we think this is going to be very powerful for software testing, but it's fully new. We just released this a couple of months back, so you're getting a head start here in understanding this. And then we can use software visualization to show the tester or developer where are interesting boundaries, and we could find interesting boundaries using these techniques that no one really could anticipate. So if you take very high values, you will get kind of switching behaviors at strange parts of the input space, and we can visualize where is the program derivative the highest, and then we can show it to you as a candidate, and you can decide if you're going to extend your testing based on this. Okay, so a little bit, the last couple of slides is more advanced stuff, but I think it's important for you to know that this is an active area of research where we are also active in Chalmers and GU. But this wraps up the boundary value exploration and boundary value testing lecture. Thank you very much.